Last time we fine-tuned BERT to give us one label for a whole sentence, positive or negative, spam or not. But here's the thing, a lot of real language tasks don't want one answer for the whole sentence. They want an answer for every word or a precise piece of the sentence. We're still living in the predict stage of our pipeline, but we're going to make predict do something richer than a single number. We're going to pull facts out of text. Think about the sentence, Apple opened a store in Paris. A sentiment model gives you neutral and walks away. But the interesting information is inside the sentence. Apple is a company, Paris is a city. To capture that, we don't want one label, we want one label per word. That's a different shape of output entirely. So we stop predicting once and start predicting structurally. Two flavors today. First, a tag for every token, that's named entity recognition. Second, a span for a question, point at where the answer lives. That's extractive question answering. Same predict stage, two new output shapes, named entity recognition, NER for short, is exactly this. Walk through the sentence and label each token. Is this word a person, an organization, a location, or just nothing? Ordinary filler? Most words are nothing. The skill is spotting the few that aren't and saying what they are. But entities can be more than one word. New York City is one location made of 3 tokens, so we need a scheme to mark where an entity begins and where it continues. That scheme is called biotagging. B for begin, I for inside, O for outside. New is block, York is ilock, city is ilock, and the word in before it is just O. The tags themselves carry the boundaries. Here's the elegant part. We already have an encoder that turns each token into a vector. To classify every one of those vectors, we don't build a network per position. We build one small classifier, a dense layer, and apply it at every single position. Keras has a wrapper for exactly this, time distributed. One classifier applied across the whole sequence, sharing the same weights everywhere. Now the second task, question answering. And the trick here is what we don't do. We don't generate the answer word by word. For extractive QA, the answer is already sitting in the context paragraph. So instead of writing it, we just point to it. Find where it starts, find where it ends, and lift it out. So the model grows 2 new heads. One head looks at every token and asks, how likely is the answer to start here? The other asks, how likely is it to end here? We take the argmax of each, the most likely start token, the most likely end token, and the span between them is our answer. Tesla was founded by Elon Musk, start at Elon, end at Musk. Done. Let's build both. The file has 2 acts. Up top, a tiny NER model, an encoder, then a time-distributed dense head, over biotags, trained on a handful of ConLL style sentences. Below it, the QA half, a pre-trained BERT backbone, its matching preprocessor, and 2 linear heads for the start and end logits. A head we already fine-tuned on a QA set and are loading back in. Notice the pattern we keep seeing. Same transformer body, swap the head for the task. Let's walk it. First the data and the tag set. We define our bio tags, O, B per, bioorg, block and their inside variants, and map each to an integer. Then a couple of toy training sentences already split into tokens, each token paired with its tag ID. This is the ConLL format in miniature, words in one column, labels in another. Now the NER model. We embed the token IDs, run them through a bidirectional LSTM encoder, so each token sees its neighbors on both sides, and then the keyline, time-distributed dense num tags, that wraps a single dense classifier and fires it at every time step. The output isn't one label, it's a label distribution for each position in the sequence. We compile with sparse categorical cross-entropy because our labels are integer tag IDs, and we fit for a few epochs on the toy set. Watch the loss drop. With this little data, it'll overfit happily, which is fine. The point is the shape, not the accuracy. Decoding. We run the trained model on Apple opened a store in Paris, argmax across the tag axis at every position, and map the IDs back to tag names. Then we sweep the tokens and collect the runs. Anything that isn't O is an entity. Apple comes out OARG, Paris comes out LOC, and everything else is filtered away. Now the QA half, we load a pre-trained BERT through Keras hub, the backbone and its matching preprocessor, which is the piece that wraps the question and context with the right special tokens and gives us a clean dictionary of token IDs, segment IDs, and a padding mask. On top we put a dense layer that outputs two numbers per token, a start logit and an end logit, and we load the weights we fine-tuned earlier on a QA dataset. That's the whole architecture for extractive QA on top of a transformer. Inference. We let the preprocessor pack the question and context together, run the backbone to get a contextual vector per token. Then the span head gives us start and end loss sheets for every token. We take the argmax of each, slice the token IDs from start to end, and detokenize. The model points at Elon Musk. We lift those tokens out, and that's the answer, never generated, just located. And there it is, two structured outputs from the same predict stage. NER gives you a tag per token, QA gives you a span per question. Both ride on the same transformer backbone with a different head bolted on. That reuse pattern, one body, many heads, is the quiet superpower of this whole architecture. Next time, we leave text behind and point the same prediction machinery at numbers over time, forecasting the future with a windowed LSTM. See you there.